One of the most important contributions to the RLVR space in recent months is, in my opinion, the maximum likelihood reinforcement learning paper, or MaxRL, from Fahim Tajwar and Guanning Zeng. It's a continuation of the line of research that is trying to understand how and why grpo works in RLVR and how to improve upon it. The core insight is that when we train the model with RL on binary correctness reward, we're implicitly defining a likelihood over correct outputs. But standard RL algorithm like reinforce or grpo only optimize the expected pass rate. This, as we're going to see, is just a first order approximation of the maximum likelihood objective. And that distinction matters a lot for efficiency and performance. What MaxRL shows is that by normalizing by the number of success k instead of total rollout n, you end up being unbiased for an objective that converges to the true maximum likelihood as you scale compute. The practical consequences of this is quite significant because MaxRL Pareto dominate grpo across multiple settings they tested like maze, GSM 8K, and post-training on billion of parameters on MAT and AMI. On top of that, MaxRL preserves pass at k diversity where other methods like grpo collapse it. And this achieves up to 20 times test time scaling efficiency gains. Overall, a very important result with a very simple mathematical change backed by a strong theory. We'll spend the first half of this video breaking down the paper in detail so you understand where the changes are coming from and why it's so simple. Then in the second part, we'll interview the first author, Fahim and Guanning, to go deeper into the intuition, the open questions, and where this line of work is heading. Enjoy! Let's see a bit of an overview of the paper, just to give you some idea. I took 3 papers that actually, in my view, helped me put this into context, the actual discovery, right? It's maybe not the paper that the guy, the first author will have chosen, but this is what helped me personally. We're going to go through some definition because this is kind of a math-ish paper to go from the preliminary element to the max reinforcement learning formulation. We're going to go through MaxRL, from theoretically what it should be look like and empirically in practice exactly how to implement it. And at the end, we're going to see a bunch of result and takeaway, which are pretty cool. Cool. So these are the 2 guys, Fahim and Guanning. The whole idea here is that it's like a convergence of multiple things that have been plaguing reinforcement learning with verifiable reward, right? This whole paper is actually trying to get the maximum likelihood reinforcement learning paradigm, right? You're going to see in a few why maximum likelihood for them was a target, but just so you know, maximum likelihood in supervised learning, it's great. It's a great objective to hit for. So that's the overall idea. If we're able to get there, we should palliate to some of the problem of RL at the moment. So they made a sampling based framework to approximate maximum likelihood. So you can't actually do maximum likelihood in RL because it's non-differentiable. So it just can't, it's not possible to do it exactly, but you can approximate it and they show you how to get as close as possible if you have more compute. So MaxRL is a framework to be able to get there. And then this framework, they tested it and they get some pretty cool result that we're going to see in a minute. But one of the results that is interesting is they get 20 times test time scaling efficiency gain compared to its grpo trained counterpart. And throughout this whole thing, you learn a bit more why grpo is working, right? I'm preparing a video also on the raft algorithm. I think very few people know about this, but it's a very simple rejection sampling based algorithm that is kind of on par with grpo in some specific instances. So that's basically the rough idea. The rough idea is that the algorithm work and it's simple and you get much better test time scaling. And it makes more theoretical senses than actually grpo. So we're not in this domain, right? We're not in reinforcement learning from human feedback for this. We're in RLVR, right? And on top of that, we're not just on RLVR. We're in a specific kind of RLVR. But the RLVR paradigm is simple. You have a bunch of training data. You sample a bunch of X from them, right? You get a policy. You have the policy here, which is your model. and then the model will take the prompt and then produce output, right? Rollouts. It will produce an output in this setup per prompt, and then these output will then be shoved into a verifiable reward system that will be able to tell the model if it did good or not on these rollouts. There's actually like a function here that will take the raw rollout and then transfer it into like a Y, which is what the verifiable reward is looking at. And then there's a RL loop here in order to make it better. Usually the RL loop is powered by grpo, but in our cases we are not in a mode of like reinforcement learning for human feedback here with the reward model. We just have a binary verifier, so it's either good or it's bad. That's it. There's a 1 or 0. So we don't have this. We just have a policy, a reference model, and this is grpo, but like MaxRL is not looking like that at all. So this is the setup. This is in the situation in which we find ourselves. And now that we have that, we're gonna look at the contribution of the other, just to have a broad overview. They have a good finding, which is like just a reformulation of the normal type of reinforcement learning, right? So the reinforce-like. It says that standard reinforcement learning optimizer optimize only the first order approximation of the maximum likelihood objective. So they actually are unbiased for the pass at 1, which is a problem that you see in GRP-like or like even reinforce-like algorithm, is that compared to the base model, pass at 1 will go much better, right? But if you have a pass at K, which is you produce K rollout and then you pick the best one, right? The base model is actually better. And we've seen that all throughout 2025, where like, if you have compute, why would you do RL? Just take your model and just run through it and then like just produce more output and you should be better. So you're scaling the inference, right? Basically. So actually with the grpo and reinforced, when you do RL on the base model, the pass at K kind of collapses and becomes a bit less good than the standard model. So like the reason for this, we're going to see it, but that's one thing. And MaxRL, what they're saying is that it is actually looking at the pass at K. They have this Maclaurin expansion of like the log P thing that they're doing, which show clearly like the pass at K element. And then the last thing, on policy estimator whose expected gradient exactly match the compute based on X. So they derive this, and then they imply that increased sampling improve the optimization objective itself rather than merely reducing variance. This is very interesting because it contextualizes all of the stuff that people have been seeing and looking at with just killing like more rollout, to not just like it is helping reduce the variance, but like it actually is drawing us closer with a MaxRL toward the maximum likelihood objective, which like in some sense we're going to see is what you would have if you were doing supervised learning with a model that is not doing RL at all, but that has like all of the good data set. This is it. And is this we're just doing that. It's the whole paper. This is the line change. I found super funny. The advantage is normalized instead by the per task mean reward rather than left unnormalized or normalized by the standard deviation in grpo. So it's like just a single line modification of the advantage calculation. But this single line will unbias the model for like a specific type of objective, right? If you look at the result at the high level, right, you have the base model here, you have the grpo in green and the MaxRL in red. And this is Quen 4b and Quen 7b. So they're not like gigantic model. They're still like okay. But you see like them at like in different benchmark. And if you do RL on it, you see the K over here increasing. And in some of them, you get like the best performance of grpo is produced by MaxRL much earlier. And in this specific case, if you look, it's kind of weird because MaxRL is even better than the base model at larger K, which like you can't technically get with grpo. Same here. I think one it is inversed. No, it's like strictly better, and most of them, right? Strictly better, or like just like really close, and it's better also at like pass at 1, right, or pass at like very few K. So yeah, like that's the setup here, is that the MaxRL is actually pretty good, and you get some nice inference time scaling over like a grpo. With multiple K, so like you can get the same performance for like less compute basically. So if you're interested into like a paper that like is diving into the edge but like is very approachable, should check out, and it's 44 pages. It's actually a little book for you. And then at the end you have like all the theorem over here. Like the two main important theorem is like theorem 1 here and theorem 2, and they're pretty simple. It's nothing too complicated. And they're like the reference in there, you should read them also. There's 3 papers that in my view were important. This one, I'm cheating a bit, but like Fahim like told me like, yeah, this is why we're doing it. It's this paper from November 2025. Does reinforcement learning really incentivize reasoning capacity in LM beyond the base model? I didn't read it in depth, I skimmed it a bit. But basically what they're showing here is while RLVR improves sampling efficiency toward correct path, we surprisingly find that the current training rarely elicits fundamentally new reasoning pattern. And what they're saying this is that like the base model achieve higher pass at K score when K is large. And one thing that they did in the experiment is they actually, instead of like doing RL, they just distilled the model into a small one. And they said that like we found that distillation can introduce new reasoning pattern from the teacher and genuinely expand the model reasoning capability. So if you look at the pass at K here for the number of K sample, the base model is in green. Pass at low K, all of these models are better, which is to be expected. But after that, like at large K, the base model is better. So it kind of means that like the model already had the answer, right? But the other algorithm are kind of like sharpening the output so that like they appear in like earlier K, right? That's kind of what's going on. But the distill model is much better than everything. So that's that. So like I'm gonna butcher it a bit, but like the idea is like, what if instead of distillation here we had RL and still we could get like the proper a better performance at like all K, right? So this was the inspiration for like doing MaxRL, and you see MaxRL is kind of having kind of the same curve, which is always above the base model. The other paper, which I covered in depth last week, in my view, it's like some of the building blocks that we're seeing here, but in a crude fashion, right? So it's the minimalist approach to LM reasoning from rejection sampling to reinforce. The whole vibe of this is like the detail is not important, but like they had 2 algorithms. They had raft algorithm, which is basically you just discard like a draft which only train on positive reward sample. So like you take only the top ones and then you just take the one that works and you discard the one that doesn't. And with this they were able to understand like why grpo like worked well, which is not like the weird normalization that is happening, but it's actually like mainly driven by like the fact that it's filtering the too hard and then too easy question, right, in some shape or form. So they propose another algorithm, reinforce reg, which is just doing this. It's reinforce plus remove, but remove like the too easy question and too hard. Too easy is like you did K rollout and all of them were right. Too easy. Too hard is like you did K rollout and all of them were wrong. It's too hard. You're not even able to get a signal out of the thing. And you just filter that. And if you do that, they actually did a whole battery of tests here. But if you do that, reinforce is in gray here, kind of suck. And then reinforce, the raft is here, right? It kind of is good up to like here. And then it's like not that great. And the reason it's not that great, it's not learning from the negative signal, because you remove always the negative one. You only keep the positive. Yeah. So, but reinforce, if you look, it's just tracking grpo like crazy. It's like actually almost grpo like, right? And then they did the kill loss and the entropy loss, but like that's one of the thing they did. So if you had this slider of K, right? You have K equal 1 here, 2, blah, 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 and -1, right? Here, it's too easy, right? This is easy. You did K and then it was easy. You do nothing. You don't update the model with this. There's no information. Here, K equals 0, it's too hard, right? So you're not taking it because there's no signal. It's just, you're just gonna tell the model to like move out of there, but no, you don't tell it where. Actually, grpo is scaling these off. Like if it's too hard, it will not update anything, right? So it's doing this implicitly. Yeah. So that's kind of the setup here. In between, you're doing reinforce, so the weight across all of these is 1, right? The core insight that my genius brain got was that MaxRL is doing this. It's the same thing as before, right? Do nothing here, do nothing at the extremity, but like for the K from 1 to n-1, right? You're doing this. You have more weight on the hard one and less weight on the easy one. That's literally what's up here. And you do that by just doing one change in the formula. You can stop watching live right now, guys. Like this is it. Like this is the main highlight that that I got out of this. And there's another important paper by Damek, Davis, and Benjamin Reck. It actually is referencing other papers that are important. But basically what they found is that you can reformulate the objective in the binary situation with RLVR, right? And they are saying that like with binary reward, like the RLVR situation can be viewed as stochastic gradient descent on a monotone transform of the probability of a correct answer, right? Given a prompt. This is important because there's a trick that they're gonna use, Fahim and the gang, in order to craft the MaxRL. And then you can use for the monotone transform, you can use any formula. For grpo, it's a specific formula, right? It's arcsine of whatever. For MaxRL, or like just maximum likelihood in general, it's log of like this probability of correct answer. And the transform associated with rejection sampling algorithm is the logarithm. So rejection sampling is like maximum likelihood here, and the associated with grpo algorithm is the arcsine of the square root. So just keep that in mind because this will pop up afterward, and this is a result that is shown in this paper. You should also check it out. Pretty good one. So yeah, this is it. So you have everything. You're well equipped. We're gonna go, and I'm gonna do my best here. So the situation we're in right now is RLVR with 1 and 0. Right? There's no continuous reward here. Like everything I'm talking about is like just correct answers. So like code, is it running or not? Math, is it good or not? That sort of stuff. So it's binary success or failure outcome, and we have some notation, right? So we have over here like y equal y star of x denotes semantic correctness rather than the exact output equality, right? So it's good enough. So it's good enough to get a +1, and then good enough to, or like it's not good enough to get a 1, so that you get a 0. And so we have that. We have the probability of the given this parameter of y given x. So we have this information, and you usually don't have y directly, right? You're not spitting out y straight up here. You're spitting out a rollout, which can be like super huge. It doesn't matter, right? Which we're gonna call the latent variable z, right? So you're sampling here from a distribution, a z given the x. So given the prompt that you're getting, you're gonna sample a rollout out of it. You're gonna sample and rollout afterward, right? Then what you do is you have like this a deterministic decoding function, which is it will find the answer in there. In this case, like it can be like a box answer from a chain of thought. It can be like checking if like you have the correct output at the end in a specific format, that sort of stuff. It's all Quen that they're looking at, so it's a box output is the way to go here. So this function, this deterministic function, is taking the z and then is producing like the y star here. That is our guess, right? That this thing is working or not. So this is what we have, and that's it, right? So what you have for the probability of correctness, so like that this is correct given x is given by this formula, right? And this is the reward thingy. So it goes 1 if like the function, like the deterministic decoding function giving the latent give you something that is like in the realm of semantic correctness over here, and 0 otherwise. And you're doing the sum of this, and this is the probability of like that latent given x. And then you're summing over everything, but you're gonna have 0 if like it's not correct, and then 1 if it's correct, and this will be your probability of like this given x. So far, like there's nothing crazy here, right? We're just doing the normal stuff. They're doing a bunch of other definition, which is the pass rate. Here you have to be focused because this definition, like you see this probability that we just defined is the pass rate, and the pass rate can also be defined as this, right? The expectation of of the success over here. So pass rate is defined as the probability that the model produced the correct answer for a fixed input x. So this will be reused afterward, and you can also define the pass at k, which is you get at least one of them out of the k that is such that it is right, semantically right. There's two framework here, right? There's the maximum likelihood framework, which only is used in a differentiable setting, and then the reinforcement learning, the classical one, right? And the maximum likelihood framework, you have this log, of this probability that we just discussed, right? And then this probability that we just discussed is actually this, which we just showed over here, right? It's the same. In this case, you have y, but you can also have like the function, the decoding function of z, which will equal to y. So this is analogous to cross entropy training in differentiable supervised learning. And then reinforcement learning is kind of the same thing, but like here we have a reward, and the reward is defined as like that, right? So the y equal y star of x. And in this case, with the latent variable, with the rollout, you have the decoding function on the latent equal y star of x, right? Like they're literally going like step by step for you. Like every word is like a little step. So this is in the binary setting, and then you get that, right? Like when you look at the objective that you're trying to optimize here, you're just maximizing the expected population pass rate directly, right? In this case, it's not that. You're trying to optimize the log of that, right? Here you have the log, here you don't have the log. That's it. You're gonna take these two ideas, and then they're gonna like knock them out together, and they're gonna try to merge them both, right? That's the stuff that we're gonna see in a second. So if you continue here, the maximum likelihood objective admit a population level expansion in terms of pass at k. This is the claim at the end, right? This is what we're gonna go and get. With standard RL optimizing only the first order term, right? So this is where they're gonna show that like the standard RL is like a sub problem of the bigger maximum likelihood objective here. So if you see that stuff, the log over here, if you take the derivative of that, you're gonna get 1 divided by p, right? And then you're gonna get the derivative of the p here. But you could see it in a different way, right? I just put it here just so that you can see some property of that, but you can also like use like one type of Taylor series, the Maclaurin expansion, in order to get this summation, right? And this summation is actually showing you something. This is a summation over a negative summation of the fail at k, right? If you were to look at this, it's just a Taylor series expansion. There's nothing crazy here. Let's look at this element first, right? This amplifies the hard problem. So if the probability of the thing is very small, it will explode it, right? If the probability of this is like it is easy to do, right? The division will be like much bigger. So like you're not gonna amplify it as much. And then you have the gradient over here, right? So whatever gradient you get here on a hard problem will go way up. Whatever gradient you have on an easy problem will go like will just be like normal. So this is important to see, and then you can see it in the other way with like this expansion, and you can see that like it actually is a summation, right? The derivative of like the objective, a summation of that optimize the infinite harmonic mixture of pass at k gradient. So the gradient at each pass at k with higher order term encoding rarer success, which are critical when p is small, right? When p is very small, they're very important. In contrast, the classical reinforcement learning approach is to optimize only the expected pass at one objective. This is like a known result. This is the derivative, right? It will be like this. It will be almost purely at the pass at one element. So this pass at one is if you had this maximum likelihood, but the k stop at one. If the k stop at one, right, you recover this result. So it is encompassed in the maximum likelihood gradient calculation here. Of course, right? So reinforcement learning optimize a first order approximation of the maximum likelihood objective. Cool, but this is not that useful, right? Like you have an infinite over here, and then you have this little guy pass at k. How are you going to estimate both of these, right? So they are hard to estimate, like when you have finite sample. If you have infinite sample, okay, cool, you can do it. Large k, it's also computationally demanding to do that. If you have a k of like 1 million, you're gonna create 1 million rollouts in order to estimate that probably. So like everything, right? We're gonna go from the theory now to like the empirical result that are good enough. Like they are good enough, and then you could increase your accuracy of like being close to that with more compute budget. So this is where we're gonna go. We're not even at MaxRL right now. This was maximum likelihood. Now we're gonna try to take this and then put it into an empirical setting. So maximum likelihood gradient that we just saw is difficult to estimate with finite sample. So they're gonna do like this is simple stuff. Like you can't go to infinity, right? I mean, if you go to 2, would it be better than if you just went to 1, right? Technically, yeah, it's a bit better because you have the 1 and then you also have the pass at 2, right? Okay, if you do it to 3, is it better than the 2? Yes, it's better because you have a better approximation. And it's just this is the idea, right? So the idea is that like in practice, you're gonna pick a t, right? A t will be like your amount of truncation from the total maximum likelihood in order to be as close as possible, right? Given your compute budget. So if it's 3, you're gonna have the gradient for pass at 1, pass at 2, and pass at 3, right? Like that's what you're gonna have in this population gradient here, right? So you pick your t, and then you're good, right? T equal 1, we cover reinforcement learning. T infinity, we cover maximum likelihood. And in between, you get something that is like that has good property, and then like will scale with the compute that you have, right? So MaxRL provide a principal framework for trading additional compute for higher fidelity approximation to the maximum likelihood objective. So that's roughly the idea. Like this is MaxRL, right? We're still in theory because like trying to figure this out, yeah, you have to estimate it, right? So now next step is this. Next step is like to estimate it. And like, how do you choose your t? This connect to like the whole literature about like inference time scaling of just like making more rollout, hoping that you're gonna get the right stuff, right? Verifying it, and then your performance should like improve with pass at like 2000 or something like that. This connected because like what it means is that if you have pass at 2000, technically you are gonna be really getting closer to like a maximum likelihood like objective. Right. So we're gonna try now to get this pass at k and find an estimator for this. And then there's a bunch of theorem. Like we can go through them here, but like you should definitely read that. Like it's like some simple calculus stuff here. Like nothing crazy here. You take the derivative of the log, and then you have that, which is 1 divided by the probability of the pass times what I showed you earlier. Okay, so we're over here. Yeah, you can check this out for the theorem, right? Going from like this population gradient formulation to that, which is what we're gonna see in a second. It's not like complicated math over here at all. So what they're saying here is that the gradient of the maximum likelihood objective admit the following conditional expectation representation. And if you see here, right, this is on the stuff that worked. Rings a bell, right? It's on the stuff that worked. So theorem established that the maximum likelihood gradient is the average gradient from successful trajectory only. And this goes back to this, right? Like all of the RL with binary kind of reward thing can be viewed as stochastic gradient is ascent on monotone transform of the probability of a correct answer given the prompt. So there's the probability of a correct answer given the prompt, and we're gonna wrap a function around that. And like MaxRL is like having a specific function in it. grpo also, like all of the even reinforce is a specific function, which is like 1, but that's the idea. So this is like an intermediate result that will help us out. And wait a second, this is it. So we have that, right? So then if we use this and we're able to somehow just get the correct answers, right? Theoretically, we can directly calculate this gradient over here easy, right? It's not difficult. The gradient of the log is not something complicated to calculate, and then we just need to do that on the positive ones, right? There's different ways you can do additive sampling here. You can do rejection fine-tuning, rejection stuff. What they decided to do here, instead of like doing additive sampling, was to sample from the unconditional policy, so the normal model, and then average over only the successful trajectory, right? You only average over there. So that's the idea, just to get like your expectation here properly. And so they fix an input X and draw n latent trajectory N. And then the reward is this, right? So like with the deterministic function that we saw previously. And then this is your scoring function, which is this gradient over here, right? This scoring function, you're gonna like multiply it with the reward, and you're just gonna average. And the k is the number of successful sample for this x, right? That's the genius idea that is happening here, right? This is good. And then we average a score function only over successful trajectory and obtain the following reinforced style estimator. You see, right? The only difference between the reinforced and this is this k, right? In reinforced, it's an n. In MaxRL, it's a k. And the k means like just like it actually worked, like this, like how much of them worked. So if you had n of 10 and then you had 3 that worked, you're going to average on the 3. If you have n of 10 and then you average on you have 9 good, you're going to average on 9. Here you're going to average on 10 all the time, whatever happens. Even if you get them all wrong, you're going to average on 10. This is unbiased for pass at 1, but this, like because of the derivation that we saw, is unbiased for this quantity over here, right? This quantity is that stuff. So this is the MaxRL that we're trying to get to, right? And then you see over there, it's a summation up until n. So we're saying that like our t, the truncation, is related to the number of sampling we're getting per rollout. So that's the overall idea. This is what they're saying over here, and then they're showing it in the appendix again over there, like why that is exactly. But like again, it's nothing complicated. It's related to like when k equals 0 and when k is bigger than 1. Because if you have when some input may receive 0 gradient, if there are no success within n sample, the result will be unbiased. Will no longer be unbiased over there, but will be unbiased related to this, right? So this is still good, and then this is still within what we wanted, because at the end of the day, we want this to be unbiased over that stuff, right? We're trying to kind of create an estimator for that. So everything is good up to that point, right? So as we increase the compute as a rollout and lead to better approximation of the maximum likelihood, as you increase the compute, you're increasing your t to be closer to like the actual maximum likelihood, right? So that's that, right? So additional compute in this specific framework improve the objective itself, not just like the variance reduction or the estimation quality or whatever, right? It improved directly the objective that is now a better approximation of like maximum likelihood. So far we're good, but what you're doing now is you're only doing it on the positive ones, right? And if you, didn't dive into this too much, but if you remember this little rafting, right? The rafting is only doing it on the positive ones, and the performance is not that great. Like it literally stop exploring. Like if you look at the raft here, right? This is the entropy. At some point at 100, it will stop exploring because it only is looking at the correct ones, right? So you need to have some incorrect for exploration. Like this is a known thing in RL literature in general. So if you have some incorrect, you can still learn from them. But in the current setup, we don't have that. Like we're not even looking at the incorrect one. And also, if the variance is high, here, if when the successful sample k is small, so like you say, you're sampling from n of 100, and then you have a k of 1. Like you can introduce a lot of variance in your estimator of the MaxRL. So what you could do instead is try to do a variance reduction, right? A bit like grpo is doing. Like with grpo, it looked like this, right? This is like how they're timing the variance with like the mean 0 stuff and then divided by a standard deviation. Is it good? You can read this paper with Dr. grpo to check it out. Actually, it's like there is some biases in this, but the variance reduction, the mean 0, is actually important. So like what they're saying is that they can use this quantity over here with this is just a zero mean control variate. So you're gonna take like your estimator that you care about, and then you do minus that all the time, and then this, because it has zero mean, it will not change the expectation of your stuff, and then you will be able to reduce the variance with this, because this will always have some quantity that you can reduce with. Doing that, right? I'm going to run you through like an example, will allow you to learn from the negative sample. So like you have the stuff that we just saw here, right? And then with the k, and then you do minus the n stuff, right? So this is a control variate that we just discussed, and you get this formula. You get basically here this. So this is like your gradient of log of this, and this is like your reward that you have over here divided by k minus 1 divided by n, which is like your control variate. Still unbiased with the other stuff because you're doing minus 0 expectation here. And then the first term, this divided by k is 0 when k is equals 0, because otherwise you're going to have a division by 0. So basically they're truncating here, right? If this is, there's nothing that worked, we are gonna like shove everything to 0. If everything worked here, right, what will happen is also you get that for free. If you have an n over here, right, and then the reward is all 1, you're gonna have 1 divided by n minus 1 divided by n, 0, right, whatever the score function gives you. So all of this will be 0, right, if you have like all of them equal to all of them, right? So you get kind of the like this for free with this situation. If we look at that very like simple toy example here, right? Let's say you have like this sample for like 1x, and then this one failed, this one was good, this one failed, this one was also a failure, and then you have this different score function. With the normal reinforced stuff, you're gonna try to do like you're gonna weight everything by the reward divided by n. So 0, 0, 0. So you're not learning from any of these, right? And you're just trying to learn from that sample that worked, right? Which makes sense, right? But you're not learning from the negative one, and they have a small weight. But this problem in general, I know it's just 4, but like it's a hard problem because you got 1 right out of 4, right? So if you look at MaxRL, the original one without the variance reduction, what we get is Ri, that's the reward, divided by k instead, right? And the k is what? The k is 1. You got 1 right. So here you get 0 divided by 1. You get 1 divided by 1. So you get a big signal here. And these one you're not learning from them because like you're throwing them away technically, right? So it's the same stuff, right? The same parameters you're gonna do here, you're gonna do much more of it, because what it tells you is that like this is a hard problem, so pay attention to that, like this specific problem, and change stuff more for this specific hard problem. With the variance reduction though, you get something different, right? You're gonna get 0 divided by 1 because you still have 1 good, but you're gonna do minus 1 divided by 4 for the failure. So you're gonna do less of this, whatever this is, right? You're gonna do more of this. It's still big number, like bigger than like the reinforced one. You're gonna do less of this and less of that, right? You're still gonna do a lot, but you're also gonna take the lesser version of it in consideration, right? And these S's is like telling you like what do you need to change in the gradient to make this more likely. So you're gonna do less of whatever this is, less of whatever this is, less of whatever this is, but more of whatever this is, and you're gonna sum all of them up to get like your final vector where you're gonna move. But like now you're learning from failure, which is something that you need in order to keep exploring. If you have an easy question now, what you get is interesting because you get like 1, 1, 0, 1. So this one is technically easy. Your k is equal to 3, your n is equal to 4. Reinforce will give you this, right? It's easy, so the success, you learn a bit from it. For reinforce, the gradient are still as big as before. They don't matter, right? Like you see here, you have 0.25, right? This is a hard question. Simple question, you still have 0.35 when you get them wrong, right? Like that's it. You just keep doing it, right? So reinforce, like the straight version of it, is difficulty agnostic, right? Do we want that? There's in the additive in the curriculum learning like type of literature, prove that like you should actually take into consideration the difficulty of the problems. With MaxRL, with variance reduction, right? You're going to do the reward divided by 3 minus 1 divided by n. But look at what's happening with the success one, right? Before, the success was absolutely huge. It's like it was 0.75. Now the success is almost doesn't matter. It's like, yeah, like it's already working, right? What should we change? Anything? It's already working. It's already working here. But like, oh, what you did here, do less, right? You have to do less of this. So you still have the penalty of doing that, right? But you're gonna like keep everything else much more constant, but you're just gonna look and move into where the penalty was. So that's the overall idea here, right? So the easy question, you're gonna like put less emphasis on this, and the hard question, you're gonna put much more emphasis on this. With grpo, it's kind of the same, but it's another function. It's not like the same divide by p type of stuff. This is just for binary, right? It's just binary word, and it has a specific kind of formulation. Continuous, I think like it's still an open problem, but these guys may be working on it at the moment. This stuff, this GN, is what you want to shove over here, right? You get the rollouts, you get your scoring here, and then you get the reward, and then based on that you create like this function. But you're just gonna do the n stuff like before, but you're gonna multiply by like the the per task mean reward. If you do that, the per task mean reward, this n become a k, which is what you need, right? You can get your k here. Yeah, that's it, right? So if you get that, right, you get gonna get this one, which is closer to this formulation that we want. And then if it's 0, right, so like the reward is absolutely nothing, then you're gonna give a 0, and then you're just not gonna take into consideration this line altogether. Like it's just this little change that we need to do. So a single line modification to the advantage calculation, and then concretely the advantage is normalized by the per task mean reward rather than left unnormalized, as in RLO, or normalized by the reward standard deviation. There's no like story of standard deviation at all. And also, by the way, in the raft paper here, they tried it, right? They tried with like this normalized standard deviation. They try a whole bunch of stuff. They try with the mean zero. The mean zero is important in some situation, but like the standard deviation is not doing much, right? It's not doing a lot of heavy lifting over there. So that's the situation. And like this section 5 is kind of the same as the other paper that I showed with like that showed like it's like there's a function, a weighting function on the probability of the positive outcomes, right? It's the same idea as this plot, but like for the derivative. And what we're seeing here is there's the pass rate, right? And it's like all of the different algorithms that you can think of, weighting function. The weighting function for reinforce is 1. Every one of them, no matter the difficulty of the pass rate, the probability of the pass rate, is 1. So even if you have a difficult answer, like a difficult question, you're going to give it like a weight of 1. So there's no difference whatsoever. With grpo, it has this form. It's the green thing, right? It's like this. So this is good. This is for the hard one. But for the easy one, there's something weird. It just spike up. So like what it means is that if it's very, very easy, grpo will kind of prefer to like increase them, which is just because of the weird weighting function that is over there, right? So this is like kind of such tricks in order to make it to work. It's a very empirical derived optimizer, right? MaxRL is like this. The maximum likelihood is 1 divided by p, right? It's like this straight line over there, right? On the logarithm. And MaxRL is like, it will approximate this given the t that you give, right? If you give a t of 1, you give reinforced. If you have a t of 2, it's better, right? A bit, right? But still, it's not like having this nice curve. For t of 128, you get very close to this, right? And as you increase, you're going to get closer and closer to that until you get like maximum likelihood with t equal infinity. So if we bring it back to the cartoonish idea that I had before, this is what we have, right? More weight on the hard one and a bit less weight on the simpler one, and no weight at the extremity. If you do it like this, it get better. And then like depending on your t, you will have like these different weighting that you're gonna put, right? We're gonna look at the result, and then I'm gonna let my guy enter. So there's a 3 experiment that, or actually 4 experiment that these guys ran. One where the exact maximum likelihood was known. So this was an image net situation, right? So it actually is not RL like, it is like more like supervised type of setup. And what they see is that with MaxRL, with a rollout of 128, you get this curve, right? Which is the validation at pass at 1, which is like good, but the maximum likelihood is way up over here, right? But as you increase MaxRL to like the rollout of 1024, you get almost exactly the maximum likelihood, right? And if you look at pass at 128, right? You get this this curve at 128. So as you increase the t, you would get closer and closer to maximum likelihood. So it makes sense. That's what they're saying. Like they're saying they didn't mess up the math. So like this makes sense. So yes, it is approximating the maximum likelihood in a situation where we have the control. In a situation where we don't have the control, so RL specific, there's no differentiable stuff. Like you can't know, but like now, because we did it with the control, we kind of know that this is happening. In an infinite data regime, so like there's always the exploration. I think this is a maze thing, right, going on. What they're showing is interesting is that at pass at 1, right, like the lower here is the better. MaxRL is dominating, right? But if you look here as the training rollout increase, like when you have more k, there is nothing that come close to this, right? Even the base one doesn't come close to it as the training rollout is increasing here. It's interesting, right? So like it means that like yes, the performance is supposed to increase with grpo and whatever. The base is catching up on them, right? This is the base model in the dotted line. But at 1, MaxRL is better than all of them, right? Like at pass at 1. So you don't need even like 248 to beat them at 248. If it literally do that, it get even better. That's what it means. So this is it. In a data-rich training regime, MaxRL scale more favorably with additional compute compared to existing method. And like from the get-go, it's still good. But you see it scale pretty well from this starting point to here. In a data scarce regime, so like you can't explore forever and stuff like that. This is the GMS 8K. What we're seeing here is that there is improvement over a large number of epoch, and this is at pass at 1. So like the pass at 1 is improving well. At 15 epoch, it's better than like grpo and RLOO. At pass at 32, it's better than everything. Pass at 22, you see the base is starting to creep up, right? But like still, the top performance of MaxRL is better than base at 256, right? That's what it means here. So even a data scarce regime, MaxRL can sustain improvement over a large number of epoch, demonstrating less pass at k degradation over fitting, converging to a higher average performance. So that's that. And then in the LM RLVR situation with like Quen 3 with the 7B and the 4B version, like you see the same story as before. It looked like the distilled version in this other paper, right? Like on a larger scale, mathematical reasoning, MaxRL, Pareto dominate grpo, show little to no diversity degradation with respect to the base model, and lead to a stronger up to 20% test time scaling efficiency gain. It's the thing to do, right? That's the situation. If you look at the gradient norm, right, what you see is that when the pass at rate is low, the gradient norm is high, which means that like it's trying to learn as much as possible for these guys, right? grpo kind of taper them off. It's trying to learn kind of like this, but I really like these ones, like the easy one for some reason. I really like them. RLO also has a similar curve, but like I really like the easy one because of this weird uptick based on this weighting that it's doing, right? This thing, it's creating that weird uptick, which is biasing it toward easy problem. Hey, how are you doing?
Doing good. How are you?
Yeah, not too bad. Perfect. We have, who do we have with you?
So I am Fahim. This is Andrea, the primary advisor on this project. And I think the other co-lead author is joining soon. Yeah, so this is Guanning.
Okay, perfect. Everybody's there.
Both of us.
Good. Maybe Fahim, you can start just to tell us a bit more about your background.
Yeah, so I am Fahim. I am now a third year PhD student in the machine learning department at CMU, co-advised by Raslan Salahuddinov and Jeff Schneider. I work on mostly LLM plus reinforcement learning. So I did a little bit of work on like RLHF for preference learning, did a little bit of work on multitask and multi-turn learning. So like you have a sequential decision making process and try to train language models to be better at it, like the Paprika work, I guess you've seen that. And yes, then I have been working on this. I also work a little bit on self-training, but in general, this broader area of reinforcement learning and language models.
Cool, great. It's nice to have you here. Thank you for coming. How do you pronounce your name? Guanning? Is it Guanning? Guanning? Guanning.
Yeah.
Got it. Perfect. Nice to meet you.
How do you pronounce your name?
Yeah, your name.
Mine is Yassine.
Yassine
is good.
Yassine.
Yeah.
Cool.
Yeah, go ahead, Guanning.
Okay. So, hello everyone. Thanks for having me here. I'm super excited to be here today. My name is Guanning. I'm a final year undergraduate student at Tsinghua University, majoring in computer science with a second bachelor's degree in economics. And I'm also an incoming PhD student at CMU and likely going to be advised by Professor Andrea. I previously worked on computer vision, especially generative models, image video generation. Lately, I've been especially interested in post-training paradigms for foundation models, such as reinforcement learning with verifiable rewards and distillation, etc., and how they trade off capability or generalization or reliability and so on. So In general, my research interest is to build principles that explain the behaviors of foundation models and their training dynamics, and to turn them into practically beneficial solutions. And overall, thank you for your excellent tutorial just now. And,
Thank you.
yeah.
I did my best. I did my best.
And I think it was very good.
Thank you guys. Like this is too kind. I was up until midnight, right, trying to piece everything together. But I think it did good. I wanted to ask Guanning, what made you switch from like the more kind of vision type of stuff toward like reinforcement learning with verifiable reward? Like what was the switch like?
Yeah, this is a really good question. So basically, when I work in computer vision, I mainly solve one specific problem, such as detection or segmentation or generation. And I feel like if I work on foundation models, I can try to work on something that is more fundamental and more general, and potentially solve a broader range of different tasks. Yeah, so that's why I got more interested.
That makes a lot of sense. For disclaimer, I come from a neuroscientific background. Actually, I was doing consciousness applied AI stuff. So I understand also the desire to go to something a bit more fundamental. And Andrea, maybe you can present also yourself. That'd be super nice.
Yeah, thank you, Yassine. So I am an assistant professor here at CMU. I am during my second year, and I had the wonderful pleasure to collaborate with Fahim and Guanning on this project. I used to work on reinforcement learning theory, but then when I moved to my faculty position, I started to work on more applied topics. And I would say in particular, generative AI, and more specifically reinforcement learning as well.
Okay, perfect. This is good. I went through the paper, the theory, my understanding of the intuition, but I think like I would like to hear from your side. Like I know there's a whole story with like the distillation element. So maybe Fahim and then Guanning afterward. Like, can you tell us a bit more about like what sparked this kind of reframing of the RLVR with binary reward objective?
Of course, I guess I will start and then I'll let Guanning continue. So this is back in last year that this paper came out. I think it also got a Muritz Best Paper Award called "Does Reinforcement Learning like is it really incentivizing capabilities beyond the base model?" And it's a pretty interesting paper. What they show is that across a broad range of tasks and broad range of models, like they did a really thorough investigation. If you train with reinforcement learning, then pass at K seems to be going down. So pass at 1 generally goes above the base model, but it is essentially losing the diversity or the coverage on like some very hard questions. And we were very curious about this question, like why is this happening? Like shouldn't RL just like learn to be better? Like why would it essentially lose coverage in some parts? And one thing that struck to us is if you look at the plot, let me see if I can share my screen quickly. So this is the plot from that paper that shows that the one thing that does better uniformly than compared to base model and reinforcement learning is distillation. And in particular, what they do is they're comparing against a model that has been distilled on long chain of thoughts from a much larger model. I think DeepSeek R1. And that is uniformly better. So you are thinking about why this is the case and what is happening. And like this is in particular distillations via running supervised fine tuning or like maximizing likelihood of the reasoning chains of the larger model. Yeah. So we essentially started thinking around that direction, and like the main bottleneck of this approach is you still need the bigger model to give you the correct reasoning chains, right? We were thinking, can you somehow optimize maximum likelihood without needing the bigger model? Like, can you somehow define the maximum likelihood objective over the model's own generations? And that essentially, like, I think, like I did have my own formulation. Andrea here did his own formulation. Like everyone in the team contributed like very important pieces, and eventually we came down to the story that is in the main paper. But like this is how we started thinking about the problem.
Guanning, anything to add to this intuition?
Yeah. So basically, it is like when we consider optimizing pass at 1, it is causing degradation in pass k. But if we optimize in pass k, sometimes we are also sacrificing pass 1. So basically, we need to define or rethink what is the actual objective that is a principled way in the reinforcement learning. Yeah.
Yeah. And I've been diving also like on the other paper that you're referring, minimalist approach to LM reasoning from rejection sampling to reinforce, and also what is the objective of reasoning with reinforcement learning. I find that there's like pieces of like your whole story in these, but like especially the one with the raft and reinforced reg, they kind of stop at like looking at grpo, right? And they stop at like when it's too easy or too hard, we're able to remove these signals that are useless. But the middle part is like everything is the same, right? And I think in your case, you were able to kind of twist it. Like, can you just tell us a bit more about like the link between these and what was in the Fandom formulation?
I guess I will take the first shot again. But I think like these are both very very impressive works, which also so these are both very impressive works that have good connections with our work. So I will talk about the first paper first, like the raft idea or like the minimalist approach paper that you just mentioned. So I think they like what their approach is actually, if I understand their objective correctly, is more similar to reinforce with without a baseline. So if you look at their code, what they do is, or like their paper, what they do is they sample a bunch of trajectories for different prompts, like a batch of prompts, and keep only the successful trajectories and try to maximize likelihood on them. So this is actually in effect basically reinforced without the baseline. The main difference between that and our work is that like you would also have to have some sort of task specific upweighting, right? Like if you have a task that has only 2 correct rollouts versus another task that has say 98 correct rollouts, the raft algorithm would essentially just average them all across like similarly. Whereas what we are trying to achieve is reward the rarer behaviors more. Like there are certain behaviors that are very rare, and we are trying to somehow extract more learning signal from it. So that is, but like it is in essence somewhat in the right direction, like somewhat in the similar direction as our work, in the sense that we are also trying to just learn from the successful trajectories, as you also I just discussed in the talk.
Yeah.
The second work I think is also very influential. It's trying to do like a theoretical analysis of different objectives. I think they were trying to like study rejection sampling, grpo, reinforce, what is the underlying objective these things are trying to optimize, and provide some estimators from certain things. I think the key difference is I think they do not make any sort of recommendations.
Yeah.
They are just trying to analyze nice theoretical properties of these things. And I think we essentially try to go from the same basic principles, like we start from first principles and try to construct like a practical objective for this sort of thing. Andrea, do you want to add something?
Yeah, I think this is kind of a good overview.
Yeah, that's good. And I wanted to ask this question a bit later on, but since we're touching on that, like in this paper, there's like this weighting function that could be anything. Like in reinforce, it's one, and like the other one, it's different. Do you think that there's maybe other ones that are as principled that could also work that are not maximum likelihood?
I mean, it really depends on what metric you are trying to optimize for. That is, I think, the understanding we came to at the end of the project. It really depends on what your goal is, and also it depends on how much compute you have. Like given a certain amount of compute, one objective might be better than the other. So I think like the decision landscape of what objective to use is is complex. Like it depends on the compute and the underlying, like whatever metric you want to optimize for. It's certainly possible that there can be other objectives that are good for like certain type of problems.
And do you think that it will also depend? Like it must depend on the underlying problem that you're working on, right? Like the distribution.
It really depends on that, and I think, like for example, I was discussing this the other day with another colleague. Like if you want a very reliable model, like you don't want your model to solve the hardest problems, but you wanted to solve, say, 3 problems with 100% accuracy, and those 3 problems are pretty easy, like it's within the coverage of the model, then maybe just sharpening on them is the right solution. Right? Like if you care about that type of reliability, you would go for some sort of objective that sharpens on the easy questions. Yeah, so it really depends on the underlying task, and it also depends on the base model as well, right? Like the model you are starting with, what is its coverage distribution? It's possible that if you have a model for which all these tasks are easy, then like one objective will work in a different way than other objective. So these things will depend on the task distribution, and it also depends on the test distribution actually, if you think about it. Like I can always adversarially design a test distribution where one objective will be better than the other. Like if you think about the GSM 8K experiments, I can just subsample the easiest questions from there and test GRPO, and GRPO will always
true. This is very but like I think it comes down to something a bit more fundamental, which is like, how do you define if something is easy or hard, or like if the model is good or not, right? Like is it too early or is it too late for the model? And like I've seen that you there is some of your work that is based on curriculum learning, right? But do you think that this would weave in some way with like this objective function, the curriculum learning?
So there are 2 things there. One is what we are trying to do is an implicit form of curriculum. So it is, I think, like it's in essence also similar to curriculum. So what curriculum tries to do is changing the, like, I mean, there are many definitions of what curriculum is or curriculum learning is, but one intuitive way of seeing this is changing the training distribution, like modifying it so that you pick tasks of appropriate difficulty for the model at this given moment. What we are trying to do is do it without modifying the train distribution. So you just sample randomly, but if you upweigh tasks that are easy or hard, right? Like you are just trying to, and you can imagine you can do it in other ways. Like I can be like, I will not upweigh the gradients, or I will not do the 1/k normalization, but I will just upsample the hard question. Like if I have a hard prompt, I'm going to sample it 20 times. If I have an easy prompt, I'm going to sample it 2 times. So I think these are all like different approaches or different ways of trying to attack the same problem. And what works best will depend on, I think, like the implementations or the particular infrastructure. Like it depends on a lot of things. We just try to provide like a different perspective of how to do it.
Right. We have a question from about like the your overall intuition about like why these other algorithms are actually not improving past that K, right? Yes, there's like the objective function and there's like the theory of like the sharpening. But what would you be your intuition in like layman terms about like why they're not doing that?
This is a very interesting question. I will give 2 examples. So one is one of our co-authors who really contributed a lot. His name is Yuda. So he recently wrote a paper on also perceptual degradation, which came before us, like a couple of months before us. And he actually made this precise argument that if you assume all tasks are independent and learning on them is independent, like learning on task 1 does not impact learning on task 2, then passed case should never degrade, right? Like if you like you should always, like the things you cannot solve should either remain the same or improve. But I think like in realistic cases of like how we do things, the tasks are not IID. Like there is generalization involved. So learning on one task really impacts learning on other tasks. And there is also task interference. Like there is a rich body of literature from earlier works that studies task interference. Like it is very likely possible that learning on one task or trying to like be very good at one task actually harms performance on another task. So these issues can be mitigated. I guess number 1 would be if you have a good data set, like broader coverage, that can slightly mitigate it. I guess over parameterization can, like if you just have a bigger model, it is possible that this issue is not that severe because the model has enough capacity to learn different tasks and still not forget like what it learned for other harder tasks. So yeah, so there are, I think, different ways of mitigating this. But what we would say is that GRPO and reinforce fundamentally has this issue of just neglecting rarer events. And that might affect it, right? Like you can maybe always find a test distribution where perfect K will go down. What we are trying to do is we are explicitly trying to reward these rarer events, which somewhat helps with like perfect K degradation. But yeah, so the task learning is not IID, I guess, is the main, and that is also in our co-authors' earlier work that shows that this is not really IID, so you can't really think about tasks being IID.
There is another perspective, if I may add, Yashin. So, so if you think about the standard reinforcement learning formulation, you're essentially optimizing the probability of correctness. Now, that objective is by definition linear in the probability of correctness. And we know that optimizing linear objectives tends to give solutions that are at a vertex, meaning that it tends to give rise to solutions where the model, like where P is either 1 or 0. This is a little bit of an hand-wavy argument, but it can be made more precise in certain settings. And that essentially means that we observe that bimodal distribution where the model either fully solves a question or it doesn't solve it. And this is something that we actually experience empirically. We do see that the pass-by distribution tends to become very extreme and goes to either 1 or 0. This is for standard reinforcement learning. GRPO, in a sense, might make it even worse because it's upweighting, the gradient in questions where the pass rate is close to 1 because of the division by sigma. And so that can provide, even more booster for the model to be fully confident. And that must come at the expense of some other questions where the model is tracking.
Okay, that's a very thorough explanation. Thank you. Thank you very much. I want to switch gears to just continuing on the intuition. How much of it was empirically found versus like you actually like look at the theory and then you derive, because like this is like one line of code, right? And you just change by the n by k, and then you take a look and you see what you got. How did it happen in the lab? Like, did you try it out a bunch of stuff and then like you formalize it?
Guanning can say.
Yeah. So basically, we first came up with the idea that we should find a more principal objective. Like for binary tasks, we can also define a likelihood. Although it is not explicit, but there is also likelihood suggests same as the image classification or other kind of tasks. So based on this, we derived compute indexed objectives that can approximate the maximum likelihood. And after that, we experimented on the ImageNet classification task, and we found that it is working surprisingly as good compared with the original cross entropy task loss. And after that, we continue to work on train on larger models, and finally we found that it is a more principal objective.
Yeah, it's actually
if I can add some stuff. So basically, the way in which this worked is, as Guanning suggested, we started to think about this formulation, maximum likelihood, and it was like, what's the difference here between a reasoning problem that has final classes like possible answers to a problem and something like image classification? Well, it's kind of the same problem, right? I have an input and I have possible outputs, and one of them is correct. And the only difference is that in image classification, you get the answer by doing the forward pass on the model. Here, instead, on reasoning problems or other control and navigation problems, it's a little bit more involved in the sense that there is some internal randomization in the model. But that's kind of the only difference. So what we said is, well, let's look at the actual difference in the loss function, and let's try on a simple example. We try ImageNet, we try on some other task. And we saw that the maximum likelihood loss was really outperforming, and RL really wasn't working. Of course, there's a difference in scale in terms of compute, also in the sense that you can do a lot more updates in ImageNet than we can in reinforcement learning training. So that kind of suggested to us, hey, we should really do maximum likelihood, and maximum likelihood essentially is just rescaling the gradient. Yeah. So that we know it pretty quickly, like pretty soon. In the project, I would say within a week maybe of starting the project. The problem is that we didn't know how to make these rigorous, because of course you have this gradient of reinforced gradient and you're dividing it by average reward, and there's all sort of correlation between the denominator and numerator, and like statistically it's not principled, right? And so we started to think, can we design a kind of different estimator that is actually principled? But what we actually found out is that you could actually produce a beautiful theory and show that the simplest thing that you could do actually has a very strong theoretical backing. So it was kind of an interplay at the point of theory and practice, I would say. But I would say definitely theory came before.
Yeah. So I mean, just to wrap it up, I think like it's exactly as Andrea said. Like it actually went through back and forth. Like I think the initial part was that we were just. I remember still like one morning, we are just trying to see what's the difference between cross entropy and RL. Like it's very common, like if you take like a standard deep learning class, right? Like you start with training some image classifiers on cipher 10 or cipher 100. You would always use expectation of log p. Like you sample a bunch of prompts, you would do calculate the log probability of the correct class and use that as your loss, like negative log probability. And you would never try to optimize probability directly, right? So that got us very curious, like why are we not like optimizing for probability? Why do you add the log? And then we quickly worked out that if you do reinforce, is the probability that you are optimizing, not the log. And that got us curious. And actually, like a co-author on our work, my good friend Naman, he was like, okay, we should really first do image classification because we were a little bit skeptical of that, but he was like, it is the same problem. And it worked out really well. Like that was something that is very fast to run and very quick to iterate. So we actually, all our estimators were first tested there and then moved to like actual language model setups or other setups because they are more compute heavy. But it was very quick to us very soon that at least for image classification. So if you think about image classification, it is just doing, like if you do RL on image classification from a model that is randomly initialized, it's essentially akin to training on very hard tasks, right? Like your task of model's task success at the beginning is like 0.1% if you have 1,000 classes.
And generalization is also critical.
And it is also the same as language models in the sense that you need generalization. There is, unlike traditional RL setups where you train and test on the same environment, here it is basically the language model setup where you have a batch of images, you keep training, and you have to generalize to a held out set. And the intuitions.
And also it gets heterogeneous really quickly because you can imagine that there's input like images where the model is proficient, some other inputs where the model is really struggling, and that's kind of similar to what is happening in language model.
Okay, this is good. This is nice to see a bit the background, and I mean it must have been exciting to see like, okay, now we got it work, and then you move to the other one quickly.
So this is one of those projects that like initially started basically between almost like a fun things to do between me and an intern, and then immediately half the lab jumped on it because we just saw what happened and it was like, wow, like this thing is really big.
Oh, this is so cool. There was one thing that happened in your analysis of the reinforced algorithm, the MaxRL, maximum likelihood, and then GRPO. But then GRPO, we saw that like it has an uptick on the easy problem, right? Was it known that much before, this was a novel observation? Because
I would assume that
it explained a lot.
Have known it. Like I think it was at least intuitively. I think there are like a couple other papers who are also discussing the population level gradient of GRPO and trying to see how does it differ from the inputs. Because I mean GRPO is really famous, right? Like when you think about it, GRPO is the algorithm that powered DeepSeek R1, which was sort of the first like big reasoning, open source reasoning model, and it started all this wave of like research into reasoning and RL. So I think I'm pretty sure it was pretty well known, or like it was definitely known. That part is not novel. I guess the interesting part is the comparison with maximum likelihood and the truncated estimators we have, and only when I think if you look at the plot that we have in the paper, only when you put them together, you kind of see the underlying structure, right? That for reinforced, you don't weight them, like the weight is 1 for all prompts. For GRPO, you have this sort of symmetrical curve where you are upweighting the hard ones, but you're also upweighting the easy ones. So That is kind of I guess it's like doing an interesting trade-off between exploration and exploitation, and whereas maximum likelihood is taking sort of a different approach towards how to handle hard stuff.
Yeah. And on the topic of exploitation versus exploration, on the minimalist paper, when they were using Raft and Raft++ and all this, they saw that like about 100 iteration, like it's kind of worse than grpo at this point because it just stopped exploring. Like the entropy loss is just like collapsed completely. But in the MaxRL, I was surprised to see that like the negative elements only get reintroduced when you're doing the variance reduction. Actually, like when it does, like when it's not there, like the negative sample are not even taken into consideration. So is the variance reduction almost actually for variance reduction, or does it also help with this exploration situation?
I would quickly answer this first, and then I guess Andrea and Guanning can add. So I used to work on, I did some work on like negative gradients or negative advantage, this sort of stuff a couple years ago. My current intuition is that the main help it gives is actually variance reduction. So, I mean, it is possible that it does other things, but my understanding is that if you subtract a baseline, that is what most people do in practice. Like the objective in expectation is the same. Only like in expectation or the average of the objective will remain the same. It is just you are reducing the noise level in the gradient. And my guess is that there are I have this simple counter experiment to think about, which I haven't done yet. But you could reduce variance by another way, which is by increasing the number of generations, right? Like just increasing more, giving more rollouts will reduce variance. My guess is that if you just increase the rollouts 1,000 times, it will probably do the same thing without the baseline. So the baseline is my understanding, at least theoretically, like from first principles, is that it's primarily helping with variance reduction, so things converge faster. Whereas if you train it without the variance reduction, you will need a lot more training or like lot more samples to get the same level of noise in the gradient. I am unclear if that actually helps with exploration, but it is possible it does. Yeah, so that is my view.
Guanning, you want to add something on this?
Yeah. So basically, I'll also work on the baseline issues in reinforcement learning previously. So from my side, my understanding is like if you use a baseline to reduce the policy gradient variance, then it is also more likely that the model have more ability to explore. So because if you, for example, if you only use the zero baseline, which means that you only use the correct samples, then it is likely that the model will fall into a local minimum or local optimum because it has high variance in the gradient update. So only if we carefully select or estimate a baseline to make the policy gradient variance minimal, we can have a more have a better training dynamics and eventually a better result.
Yeah, I think exploration is also hard to quantify or define. Like I just
True, it is.
Exploration itself is people use the entropy, which I mean entropy is like the entropy level decreases, and that is one measure of I guess how well the model can explore. Which we do see MaxRL harms entropy much less than like if you do grpo. But I have a counterpoint in the sense that like bigger models naturally have much lower entropy. If you take the same sequence of tokens, like bigger models are generally like if you have double the parameter count or 4 times the parameter count, it is in general just much more confident on the responses. But does that mean it can't explore? That is not true. Like you definitely RL on larger models is better than RL on smaller models. So so I think like just quantifying what we mean by exploration and like some sort of like realistic measure for it itself is a good question that should probably be researched, or maybe there is research on it and I don't know.
Okay, this is good. One thing I wanted to ask is like you've done the especially on the RLVR with LM, right? Like you've done, I think 128 rollout, right?
So
If you
for
were
the larger
to,
experiments, we do 16 actually. For the GSM-8K 0.3B ones, we are using 128. But for like a 4B model, we don't have the compute to do 128.
okay, but like, do you think that you still have like a massive amount of gains if you were to kind of go, I don't know, to 1,028 over there?
I don't know
Or will it taper off a bit?
I don't know it conclusively, and I also don't want to speculate. So I think like, I mean, we would, someone with the compute at a bigger lab can probably try it out. And
We will be very curious to know the answer to that.
we'll be very curious to know. At least for ImageNet, where we can keep increasing the rollouts, we see that there is gains until like you go to 1024, and then because then it basically becomes cross entropy, and there is also limits to what you can gain, right? Like it will probably not go to 100% because I mean there is model capacity issues, there is generalization issues, and there is also definitely like saturation at some point. But in ImageNet, we saw that up until you increase the rollout to 2024, you keep seeing gains because it becomes closer and closer to cross entropy. But beyond 1024, I mean, it is upper bounded by 2 cross entropy, and just increasing rollout is not gonna increase. So it is possible that something similar happens in language modeling.
Yeah, and like, how much gain do you think there could be on the size of the model? Like just having a bigger model and then using MaxRL on it versus GRPO. Like as the model is bigger, there's
that the gains on 4B is larger than 1B. I think if I remember the plot correctly. But beyond that, again, like we would have to either run it or like hopefully someone with more compute can run it and validate it.
It also
like
depends.
it's hard to be speculated.
We can't speculate. Big boys. But it also depends on what process has been done to prepare the model. There is all this mid-training that goes into the preparation for the model before the reinforcement learning phase. That might make it easier for for instance, standard RL to achieve good performance in a short amount of time, or maybe it would benefit MaxRL more. This we don't know.
And also, like I think the amount of compute is really a big thing in the sense that. Like if you remember the overtraining experiments we had, like keep training for 50 epochs, at least until like 20 or 30 epochs, GRPO is actually still better. At least pass at 1. Like pass at K, it's worse, but for average performance, it's better. So if someone has limited amount of compute and just wants to get the best average performance in a short amount of time, I would say GRPO or reinforce or some other variant might still be preferable. So I think, so it is a function of how much compute you have, how much you want to train, what task distribution do you care about? Like, do you care about only solving the hardest questions, or do you care about solving easier questions? Like in practice, I can even imagine having like an ensemble of models, right? Like for a practical system, you can train some model to do really hard tasks and train some model to do like the simpler tasks, which can be also cheaper and smaller. And you can have like some sort of a router that picks which inference request to go to for which
depending on the difficulty.
You can somehow try to estimate the difficulty and choose the model on an adaptive basis. So I think like a realistic production case would have much more complexities that obviously we can't study. But this is like I guess the principal way of thinking about it.
Good. So if somebody has access to massive compute, try it out. Let us know.
One other thing I would quickly mention is even if you have massive compute, like in that scale, there are certain other things you probably also need to do. Like these are things we tried out, but did not make it to the final paper. But I guess we can talk about it a little bit. Is the 1/p thing, right? Like you have 1/p. But like imagine you have a model and you are generating, 128 rollouts or like 1024 rollouts, and one of them is correct. So ideally, in our case, you would upweigh that gradient by 1024, which is a massive gradient. The only issue there is you don't know whether, like just based on the final answer correctness, you don't know if the model got it actually correct or it just hallucinated the correct answer. Because it's such a rare event. In which case, you would have to either have a more robust verifier, like other than just final answer, or you would have to somehow clip the upweighting term. So we are directly upweighting by 1/k or 1/r min, but maybe you want to do something like flip it to some low, like some maximum value of how much you can upweight. You can also do adaptive sampling, like things where you want to generate multiple, like for the harder prompts, you want to keep generating until you see like k correct rollouts, which is also like the rejection sampling variant that is described in the other two papers you mentioned, like that
Yeah.
we have interactions with. So all of these things will probably be used in like a production system, and yeah, so those are like if you just keep increasing rollouts for language models, there are like other issues you might fall into. So you need like more checks and balances to kind of robustify the system against like hallucinated answers. But yeah, so I think in general, we kind of avoid that by just truncating it to 16 rollouts. You are never going to see something that is truly rare and hallucinated. The other way is just keep increasing batch size so that noise is kind of just gets cancelled out by having like a lot of prompts. But yeah, so those are practical considerations you have to have when you're trying to scale this.
This is good. And I want to kind of connect it a bit with like specifically your previous work with Paprika. I know that you were like looking at like curiosity driven learning and like stuff that is have a high learning potential and like lower learning potential. How does it disconnect with like MaxRL and like the idea behind it?
I mean, MaxRL in some ways is, so I mean, it is interesting. So in some ways, what Paprika was trying to do, if I remember correctly, is it is trying to upweigh, or like it is trying to sample tasks with more variance. So I mean, the idea, this is also true for LLMs, and like it's kind of similar to the adaptive sampling thing I just mentioned. You ideally want to have higher variance in reward, right? Like all rewards collapsing to 0 or all rewards collapsing to 1 means that the model either can't solve it at all or it can solve it always. What you want is some, like RL is trying to learn from the model's own generations. So what you want is kind of a good spread of the reward, right? Like if there is some that are very high and some that are very low, that means that you can somewhat try to push the model towards a higher distribution, but you need certain variance gap in that. So for Paprika, we were trying to directly explicitly optimize the task distribution based on that reward variance. This is not trying to do it. This is just trying to upweigh very hard tasks. So it is pretty different. But I guess like you can also bring in some of the ideas of like adaptive sampling, for example. Like maybe if you have hard tasks and you want to see more correct rollouts, you should allocate more compute there. If you have an easy task where, like, say you have generate 5 rollouts and all of them correct, you don't need to spend a lot of compute trying to get more rollouts, right? Like some form of adaptive sampling or like task selection can also come into play. But yeah, I mean, we leave that for future.
Okay, cool. Yeah, also like I think in the 2024 ICML paper, you were talking about like the fact that like two things were important. I think if I remember correctly, like the on policy learning is super important, and the negative gradient matter, right? Do you think there's still work to do on the negative gradient part to weave it in? Because right now what you did is like you made the on policy thing, and you said like this objective is actually somewhat better than these other ones, right? You took a principled stance here, but for negative gradient, I feel same thing. I feel like just because it comes from the variance reduction, I'm like, there's maybe another way that you can put it in that is as much principled than the rest.
I would just say this, this is really in Guanning's ballpark because he has had amazing work before on this. So as you exactly just said, so my current understanding is that negative gradients or the baseline subtraction is really helping to reduce the variance of the gradient, like reduce the noise level. That is the key principle, I think. Like in expectation, you are trying to take the same gradient steps, but you have finite number of samples and finite batch size. So there is always going to be some amount of noise in your gradient, and the whole purpose of baseline subtraction and all these techniques is trying to reduce that noise level so that you can converge faster, like you can learn faster. And there are like, I think, given that first principle, you can do a lot of things in trying to improve the baseline, like how do you incorporate negative samples or these sort of things a lot. And Guanning has amazing work. Guanning can also, I guess, like share your screen and just show it a little bit, like the main idea in short, and that can be pretty helpful.
Okay, this is another work. In this work, we discussed the variance reduction effect of during the policy gradient update in reinforcement learning with verifiable rewards, and we derive shrinkage baseline which can outperform the ordinary baseline of grpo or some other other algorithms such as reinforce plus. So I'm not going to go into details of the derivation. So I just will just illustrate from a high level. So from a high level, the role of the baseline is to reduce the variance of the policy gradient. Intuitively, it is trying to leverage the negative gradients to teach the model to avoid going into those patterns which will get a zero reward and will fail. So from the mathematical side, it is like the policy gradient is more close to the ground truth objective of optimizing in the reinforcement learning. And this is just like a two sides of the same coin.
Just to add quickly to that, Yasin, and make it simple for the audience, what this paper is trying to do is they calculate a baseline. So generally you have a prompt, you have a batch of prompts. For each prompt, you generate many rollouts, and the baseline is calculated per prompt, right? Like, so each prompt gets its own mean reward as baseline, which means that if all rollouts are wrong or all rollouts are correct, you have no gradient because the baseline would be 1 or 0 and you just subtract it. What this paper is trying to do is that their baseline is a somewhat linear combination and the weights are determined by some theory, but ignoring that, it's a linear combination of the prompt specific mean and the batch specific mean. It is also in short like a similar idea where if you have a prompt that you can't solve at all, but the overall performance in the batch is greater than 0, that means that you should actually negatively penalize those rollouts in some way. And you can calculate a baseline based on this batch specific mean and the prompt specific mean that theoretically gives you a lower variance in the gradient.
Right.
And it does show some like some interesting empirical results in terms of lowering the variance and also better performance. Like in short, it's basically this is already one existing work coming out of this lab from Guanning and my friend Gaman and Andrea, and I think Zhao is also on this work on trying to how to get better like negative gradients in some ways by like basically designing things that will reduce the variance even more. And I guess there is interesting things you can do.
So it's really the variance that is the key here, right? Like they're like taming it and making sure that it stays.
Because in expectation, you generally always you don't want your gradients to be biased, right? Like biased gradients are generally bad because biases can accumulate and in the end your model can just collapse. You ideally, I mean maybe that's not true, but at least true for our experiments. You want your gradient to be unbiased, like that the estimator of the gradient to be unbiased, in the sense that in expectation, it should be the same as the true gradient. But the variance is really the key, right? Like you can have the same expected gradient, but so much noise that the model never learns to converge or converges very slowly. So the negative gradient is trying to help you trim the noise from the signal, and there can be more interesting work in trying to see how you can reduce it even more. That sort of thing.
I would also add that those variance reduction schemes, they're like a free lunch in a sense. So for one, they're kind of always needed because no one runs standard reports without the baseline. It just doesn't work in practice.
It also collapses.
It collapses for those reasons. The baseline is almost always used. I would add that it's a free lunch because whenever you say I have an estimator that is unbiased for the same objective, but lower variance, that essentially means I can achieve the same accuracy with fewer samples. And in this case of training reasoning model, it means with less compute. And normally those baselines, if you design them correctly, for instance, they don't have any hyperparameter to tune. And so they give you essentially a saving in computer that is free. You just need to implement it and the system works better. So,
okay. Yeah. I'm going to read the paper next. That's the next one on the list. This is good. I want to go because like all of this work, this current work is bounded in the binary setting, right? The binary reward setting. How different here it is on the continuous side. Are you guys working on that right now?
Yes.
We are, and I think like the main difference is that in the continuous setting, it's no longer like a simple classification problem. So like maximum likelihood, like it's harder to define maximum likelihood. So you have to somehow generalize it across a different axis. And we have a couple of ideas. We are trying them out. If something works out, we will ping you, and hopefully we can do another session on it. But yeah, we are definitely interested in it, and I think that is like my understanding is that for most practical systems, right, like the largest frontier models or whatever, no one really trains on binary rewards anymore. Like I mean, that was the thing. Even the updated DeepSeek R1 tech report mentions like 4 other reward components added. Like you have the format reward. You have like sometimes their model starts speaking in Chinese, so you have to like add a penalty if it speaks in a different language, those sort of things. So the ultimate reward people use is always non-binary. And in order for MaxRL to be actually applicable for the most practical, like the cutting edge systems, it has to be generalized to non-binary setting. And that is what we are looking into, and hopefully we can figure it out.
Cool. This is pretty good. And to wrap it up, I wanted to ask you, generally speaking, like, what are you excited about, and like, which research direction is the most interesting for you in the short term here?
I think, like for example, very long context, long horizon RL is still interesting and not as much explored in academia. Like there are some wonderful works from CMU and our colleagues. Like last month, we were also studying this problem of can the model think, summarize, and then keep thinking. There is some similar related works from I think Mila and some other universities. So like, how do you really let the model do discovery itself? Right? Like you should be able to practically give the model a task and just go to sleep, and it should be able to keep thinking, summarize, do context management, call tools, do whatever else, and come up with a solution if a solution exists. That sort of thing is, I guess, underexplored in academia. Visual reasoning is, I guess, another problem. Like, can you reason in images, or like, what's the most efficient way of doing it? What is the best way of doing it? Those sort of things, I guess, we are all interested about.
Cool. And Guanning, what on your side? What's the most exciting?
Yeah, I think visual reasoning is very exciting, and I think another perspective is like the data is also very, very important in reinforcement learning training. So basically, imagine you are only optimizing a fixed set of data, then the signal you can extract from this fixed data is limited. And usually the data is the actual bound of the training for the current large-scale reinforcement learning. So if we can design some paradigms to do some form of data augmentation, or let the model to generate some training data by themselves and to evolve during this process, then it could largely increase the ability upper bound of the reinforcement learning process.
True. Because you could see it as like generating a curated data set, and it's directly trained on it, but like it's creating that data set so that you can train.
And also,
Andrea,
some amazing works already that tries to convert like unstructured data from the web into like RL tasks. Like there is like, maybe you can look up like what people are doing in the web and try to make a task that you can then give to a model to like test it, get its hands dirty on. So those sort of things, right? Like you have to somehow create the data flywheel as well. And like static, like there is also amazing works I think recently that are trying to do like similar sort of things. So like in general, just like getting rid of the data bottleneck, right? Like I think training on static data sets can only take you so far. You have to somehow adapt the task distribution, even the difficulty distribution according to what your model can do right now. And that is actually also mentioned in the conclusion of Paprika. Like the real way to extend it would be, the Paprika trains on 10 tasks. How about you train another model, or like you have some sort of pipeline to keep generating more gains? Instead of training on these fixed 10 tasks, you can keep training on different. So those sort of things, I guess, would be interesting. As Guanning mentioned.
And Andrea, do you have something to add here?
Well, we have many things, many exciting things going on in the lab. So I would definitely say discovery. So think about give you a really hard problem, and that is much harder than anything the model has seen. What do you do in those cases? Think about scientific research, right? You have to produce actual knowledge, and it's a very non-linear problem. Like you have to be extremely creative. You have to come up with novel ideas, and maybe you have to keep thinking for a pretty long time. How do you design a system that is able to sustain, this research and discovery for an extended amount of time until it actually produces new human knowledge? This is quite different from what we conceive as reasoning today, right? This is really, I have a single problem and I want to keep moving resources and I want my model to eventually do better and better. Think about if I'm writing kernels, I want to discover something like, flash attention 5. And we want that to come automatically from the model. So that's an exciting direction. And then one direction that we are starting to work in, actually, I think, Guanning will be one of the star people leading it, is about spatial intelligence and visual reasoning. Think about reasoning in multiple modalities, so combining text, but also the visual component into a reasoning process. I think we're not there yet. I think current models, they still do, they're still beginners in the visual domain in some ways. And also, whenever you talk about multimodalities, the training is often language-centric, in the sense that you start from a pre-trained language model, and then the visual component is like an add-on. But somehow, maybe that's not the best approach to do multimodal reasoning. And so that's another, interesting direction that we are exploring. And then I would say generally reasoning in non-verifiable domains. For instance, models are still struggling with factuality. Like think about even writing a mathematical proof. This is something that the models are still struggling a bit. And there's no notion of verifiable reward in that case, because either you have a human checking the proof correctness, like in the entire correctness of intermediate steps, otherwise it's not so clear like how you would go about training the model. But such type of reasoning is ubiquitous. Think about not just mathematics, but even like in law or other disciplines. And this is something that even frontier models, I think, they're still struggling. And then think about, scaling those systems to something substantially more complex. So think about if I have to design a complex product like an airplane, for instance. So how would you scale, the reasoning component of the model so that it can handle a project of that scale? And, if you look at how humans do it, there's some hierarchical structure. They have a company and there's a CEO and there's different teams that work together. And that kind of suggests you that this paradigm of having a single model with a monolithic chain of thought, maybe, it won't bring us there and you need something that is different.
Yeah.
And we have some cool works from the lab on multi-agent communication and things coming up
soon.
Nice. Cool. Looking forward. On the topic of a very hard problem, would you say that trying to derive MaxRL was a hard problem? In retrospect and right now when you know the path, would you say it's a hard problem?
That's a good question.
Because in my view, every time
what do you think?
Go ahead.
Go ahead.
In my view, every time I had to do a hard thing, most of the time I was just dumb and I was going into the wrong direction. But once I saw the path, I was this was so obvious in retrospect, and then the problem just collapsed, right? In terms of difficulty, there was no way I would have done it kind of in a different way at this point. It's of course you do these 3 steps versus trying to do these 17 random steps that I was trying before. So what do you think?
Part of that is also knowing to explore and tune out that part, right? You have to somehow understand that. It is true that once you know the solution, it's kind of obvious, but coming up with the solution, making the connections between the different fields or different things, to somehow get a conclusive idea is, I think, still difficult, and also probably difficult for models.
Yeah, I would say it's kind of a difficult discovery at this point still. The primary reason why I say that is my experience, because I actually use ChatGPT heavily for this project to kind of, for formulation and everything. And you have to put it on the right path. So you need to have that initial intuition and believe in the idea, and then keep moving forward and, analyze the estimator and see in what direction do you even want to go, basically. What are the interesting properties that you might be interested in proving? What is the desiderata and all those things. The models, they don't have that taste yet. They can kind of prove a statement once you've given it to them, but they don't know in what direction to go.
Yeah.
They don't know what's good, right? That's where your taste and
I was
sensitivity comes in.
Say the same thing.
And it was absolutely critical for this project.
My understanding is that these models are very good at like writing a proof or like doing a math problem that has a final answer, but they don't know what problem to do. I feel like that.
Yeah, I think this is it.
If you try to give it, say, a thing and say, find me a generalization, most of the generalizations we did find are like mostly garbage.
Yeah.
So you'd have to know in what way you want to generalize and what is the final thing, like that kind of way, envision it, and then it can fill out the intermediate steps on like how to do it.
Yeah. I think it's true, because when you work on a hard problem and you're like 7 step deep and there's nothing that's moving, you have to stop, right? The model will just keep going, right? And once you find like 2 steps that are working, that like it's close, right? There's a feeling of like this task, this hard task is decomposing on like these 4 steps that one might not be obvious in retrospect, but now is, because you actually tested it and now it works.
I would also add another thing, that those systems, in large part, they're like doing statistical pattern matching. And so if you somehow ask the model, hey, why don't we do maximum likelihood instead of reinforcement learning? They will say, obviously that's a terrible idea, because
exactly. They're like, what are you talking about?
This against the entire pre-training knowledge that they have about that, right? And so it takes some courage to kind of believe in the idea and convince ChatGPT that, hey, you can actually do it because this and this and that, and then you can add in with some details.
Because you're going against the pre-training distribution.
So I think like the other example that I always had in mind is this was something that was being discussed in Twitter a couple of days ago. I don't remember whom, but they were chatting like the true test of AGI is that you train it on knowledge up until 1904 and ask it to make special relativity, right? Like, so I mean, special relativity I used to study physics at some point. So, I mean, Lorentz found the Lorentz transformations of space and time before Einstein did special relativity. He just didn't realize what it means in some ways. And also, the beauty of Einstein is not to some extent the math. I mean, the math is good, but his specialty was the courage. At least according to me.
You have to believe.
It is my understanding. I might be awfully wrong, but he literally took the step to say that, Newton's formulation is limited in scope and Maxwell's one is correct. So I'm going to build a special mechanic, like entire field of mechanics around like that understanding. And I think a lot of people could have probably done the math, but no one believed in the idea, and people thought it's ridiculous to go against Newton, right? Like, why would you are in 1900s, Newton is a god, and why would you think that Newton's mechanics is
and it's
wrong?
Not even something that you can test easily.
Yeah. So that is the part I think it's probably still harder for models to do, but we'll see where it goes.
We need contrarian models. That's the end of it. Okay, great. I don't want to take too much of your time, because you guys have work to do. So thanks a lot for coming. That was really awesome.
Thank you for giving us this opportunity to talk about our work and featuring your website. I think it's really amazing. Thank you for all your hard work. Like, you also put in so much work in trying to
read all those papers.
Read all these papers.
It's so cool. Like as soon as I found a good one, I'm like, okay, well, like there's clearly something in it that is like fundamental. And this one, I saw it directly, and it got me like reading all of this other literature that I was not like 100% familiar with. But now I have a much better understanding about like this whole RLVR field. Well, thank you guys. This was absolutely amazing. I'm going to put like all of the information in the description. And yes, thank you. Have a great rest of the day, guys.
Fantastic.
Thank you. Thank you, Guanning, for staying up so late.
Thank you.
All right, true. Thank you. Bye. Okay, that was absolutely awesome. Not only for you guys, I absolutely loved it. It's also super nice to be able to see, because I'm a neuroscientist at heart, right? And I like learning, and like the process of getting to a discovery like this, right, is not obvious in the paper. But when you get the intuition from the author directly, I don't know, I find it super exciting. And that's it. I hope that this was useful. Don't hesitate to drop a question down below if you have any. And I wish you all a great week.